Well, good evening. Welcome to Space Oddities. Thank you for being with us on this Tuesday evening. Hope everybody's well, and I hope you've all had a fantastic week. And there were a few of us here tonight. So let's just say hello to everybody. Hello, Michael.
Hi there. You all right?
Hi, Daz.
Hello there. Hello.
Roger's with us, as always.
I do hope so.
Like the proverbial bad penny.
Yep.
Pete, how are you?
Not too bad, thanks.
Good. Aaron, nice to see you.
Doing wonderful. Good to see you all.
Good. Nice to see you too. And right at the bottom, so to speak, is John. How are you, John?
Good evening. Yes, very good, thank you.
Good. Have we all had a good week?
Yep.
Yeah.
Mm-hmm.
Anything in the news that's impressed you this week?
Oof.
Astronomically speaking, of course, not.
Of course.
Of course.
Is that an open question?
Yeah.
Well, it's I think the fun one was the strange noises on the Stuckliner.
Yeah.
That was very strange, but turns out it's possibly another fault with the communications, not possibly with the Stuckliner, but with the ISS. So it's
just for those of you out there who don't know, there was a rather ghostly sound coming over the speaker of the Boeing Starliner at the ISS this week that sounded like a really distorted submarine sonar. It was quite spooky, actually. You can find it on YouTube.
Aliens.
You look for it.
Aliens.
It was really weird. But they've narrowed it down to some sort of feedback between the various communication systems on the ISS. It stopped doing it now, which is a shame because I was going to let you all listen to it tonight. But as it stopped, there doesn't seem much point. Certainly weird. Let's hope it's not an anonymous sign of things to come with the undocking and the landing of the Starliner. Speaking of which, we will be covering finally we've got a few events live this week. On Friday morning, we've got the launch of the SpaceX Polaris Dawn mission, which has been put off, cancelled, postponed, as you probably know, several times now. So the latest date is Friday morning. If that holds, we'll be going live here on Friday morning at 7:15 BST, UK time. So we hope you can join us for that historic mission that we've talked a lot about, and we have videos on the channel about it that you can find. But really an historic space mission launching Friday morning. And then later on Friday night, we have the undocking of the Starliner from the ISS. Now, we don't normally cover undockings from the ISS because, frankly, there's not much to see except a spacecraft sailing off into the distance. But this one is important because of this disastrous mission that Boeing have mounted to the ISS, marooning 2 astronauts on board for 8 months instead of the stay they were expecting of 8 days, and the problems with the Starliner. And now the Starliner is returning to Earth without the crew because NASA have decided it's not safe to put them on the Starliner for the journey home. They're going to have to wait till February till the SpaceX Dragon can come up and fetch them. The Starliner will be running autonomous software as it undocks, which has never been actually tried in anger before. Everything we hope goes okay, but there is a small but nonetheless significant possibility that something could go wrong with the Starliner again and its thrusters and its helium leaks, which could turn into a disaster. Worst case scenario, it could collide with the International Space Station, which will be a major disaster. So we hope you can join us for the undocking of the Starliner. Obviously, we hope everything will go well. And we are starting that coverage on Friday evening at, what time was it? Can you really remember? Was it 10:50 UK?
Well, I'm starting the show. I think you said 10:50. Yeah.
Yeah, 10:50.
But the undocking is just after 11 or something, isn't it?
Yeah. I think 10:45 is on the channel. The time will go live, and we hope you can join us for that. Several hours later, early Saturday morning, will be the landing of the Starliner. Now, we know that the Starliner's had problems with its parachutes before, so let's hope that that goes well, and that will finally be the end of this disastrous mission, which has led to NASA getting much egg on face and embarrassment all round that this situation could ever have been allowed to happen in the first place. So I hope there's going to be a full inquiry about this. I'd be surprised if there weren't. So, what should have been a normal mission that SpaceX run all the time, ferrying astronauts to the space station, has turned into a disaster. But enough about all that. We hope you can join us for those 3 live events later this week.
There's 6 hours from undocking to crash down, because it's not splashing down, it's crashing in the desert, so it's got to be a crash down, isn't it?
That's right.
Well, hopefully it won't be, but it'll be a gentle poof.
Yeah, absolutely. So there is that. Just give me 1 second. I appear to have lost my mouse.
Well, while you're doing that, Andy, let me just share something with the crowd.
Certainly.
I received this through email. It is a comic, so know that it's supposed to be funny. And it's a picture of NASA, I guess it's the control room, with 2 people there. And one of them is saying to the other, he's got a phone in his hand, by the way. He says, Boeing says we forgot to check the box specifying round trip.
Yeah, I did see that. Yeah. Check
Oh, cutting.
You didn't book a return ticket. It's like Aer Lingus, isn't it?
Yeah.
All their flights are Ryanair. All the tickets are one way.
Yeah, it's like smoking or non-smoking.
Right, mouse restored. I made the mistake of buying we got a cheap supermarket here in Girona, and I made the mistake of buying a pack of batteries for use with my mouse, and it was 10 batteries for €1. And I thought, oh, that's good value. And now I know why, because they only last about 4 days. So I've just replaced the battery and we're fine again. There's much embarrassment and hilarity about the whole Starliner thing at the moment. But as we know, it's a serious business. So let's hope everything goes off.
I think that the we can laugh about it really now, in the fact that we know that the crew are not going to be on there.
Yeah, that's true.
So I think that was what some people's my concern was. They would be daft enough to insist that they come back on there, but basically common sense prevails.
Common sense has prevailed, absolutely.
Yeah.
Okay, now coming up in tonight's show, most of tonight's show, I'm going to be talking to you about Big Bang Theory. We're going to delve into it, what the Big Bang Theory says, how do we know what we know, and I'm going to give you quite a detailed timeline of what we think happened after the Big Bang up to the present day, basically. And of course, if you have any questions about Big Bang Theory, please put them in the chat, and we'll answer them after the presentation. Okay?
So we have to call you Sheldon.
Yeah, I was going to say the first person, when I say Big Bang Theory, to mention a certain American TV program will be on mute for the rest of the program. So that's your first warning, Dan. So let's have no more mention of that. Okay.
We'll call you Penny. We'll call you Penny.
Right. I have no idea what that means, but if it makes you happy, carry on. Okay. Right. So we've got that coming up. We will, of course, be having Daz's Solar Watch. Daz is going to tell us towards the end of the program about what's been going on with the sun this week. We have Roger's, of course, without which the show would not be complete. Roger's Sky Guide, and the Viewers Gallery. Do we have a big gallery this week?
Oh, we've got a normal gallery. We've got about half a dozen images to put up for this evening, so not too bad.
Good.
Quality, not quantity.
Right. Okay. And we'd just obviously finally like to say thank you to all of you for watching. Thank you for being here. And don't forget that if you would like to help us keep Space Oddities going, you can buy us a coffee, and you can scan the QR code here. And if you buy us a coffee, keep our caffeine intake up to its normal high levels, we'd be very grateful. All money received goes towards keeping Space Oddities on the road, because we have bills to pay like anybody else. Nothing is free, obviously. So thank you very much for your generosity, and thank you to those of you who have donated to us and bought us coffees week on week. We are very, very grateful. The link to go to Buy Me a Coffee should have also just popped up in the chat. Of course, summer is drawing to a close, but don't forget, we still have the Space Oddities merchandise available. We still have those glorious T-shirts and hoodies available in 2 designs from Space Oddities. The link is there, and again, it's popped up in the chat. So if you would like to buy a T-shirt to see out the remainder of the summer, although in Britain that's probably no difference, then there you are. And of course, it's always advisable to start buying them for next summer, because our supplier will almost certainly introduce a price rise, as they always do at the end of the year. So now's the time to get them while they're this price.
Yeah,
so
Christmas presents.
So there you are. So we'll just give you a quick rundown of the hoodies. There's the hoodies, 6 colours available. We've got the original T-shirt, 10 colours available. And yeah, the one that Daz is wearing at the moment.
Retro.
No, I'm not wearing that. No, I'm wearing my SpaceX T-shirt. Yes, I do have a SpaceX T-shirt.
Is that your day job?
Yes, it is actually.
I'm
I'm slumming it here, mate. I tell you, really slumming it. We have the glorious new design for the Space Oddities T-shirt, and these are available in black. And we have the same design in the hoodies, and we also have a lapel design T-shirt where the logo is on the lapel. And these are also available in a long sleeve version, for which you pay an extra £3. So the price of all these, the T-shirts are £25, including UK postage and packing, which is a damn good deal if you ask me. And the hoodies are £40, including UK postage and packing. If you're ordering from outside the UK, please add £10 to the total value of your order. And thank you very much indeed. So let's move on. What we're going to do now is...
Just before you go on, Andy, there's a question regards the Starliner and that. Ian says, will they be the longest people in orbit?
No, definitely not. The Russians still hold the record for that. I think they had cosmonauts in space for over a year, didn't they, Michael?
Yeah, you got to remember the year in space program as well.
Yeah. I think the longest chap wasn't he the one who got stranded there because of the Ukraine. Conflict.
Yeah, could be.
He was up there for a very long time. I think he takes the biscuit. But there's been several people who've been up there longer than a year and done long terms up there because they're doing long term studies. Because one of them wasn't the twins, one of them, and one of the twins was up on the International Space Station for a year, and then they compared their genetic makeup afterwards, and they found.
But don't they increase in height as well? Talking of the longest people.
Sorry?
Don't they? Don't people have an increase in their height?
Yeah, because there's no gravity. It's the same when you get up in the morning. You're always about a centimetre taller because the discs in your spine actually stretch. They're like sponges, and during the night they open up again. So you're just that little bit taller when you get up in the morning. So it's and then that's during the day they sort of slowly compress and then so on. So
absolutely. It was the Kelly twins, of course.
That's right, Kelly. Mark Kelly, wasn't it?
One of them's the one who's, I think it was the one who went into space. His brain was so affected that he ran for Congress. Terrible state of affairs. So there you are. Okay, so can whoever put that there get rid of that message, please?
Must be me.
Okay, right.
It's all right. Let me do it. Right, there you
go. Sorry, Tess.
Okay. So will they be the longest people in orbit? I'm pretty sure some people were taller. So there you are. Okay. All right. So let's move on. We're going to go straight to the news, and then we'll come to Roger afterwards. So let me just sort myself out here with the news. Give me 1 second, please.
Makes yourselves.
Okay, right. So can everybody see this?
Yep.
Yes.
Yeah.
Okay.
Yes.
So some lovely images to start the news with this week. Juno has made another close flyby of Jupiter, and it's sent back some glorious images. So what about this one of Io above the clouds of Jupiter?
Lovely, isn't it?
Ooh.
Isn't that beautiful?
It is.
It's like,
Absolutely.
like the Death Star.
Yeah, that's right.
That's no moon.
No, that's Mimas. Saturn's moon is the Death Star.
I'm assuming
And that's-
then you would call that, because you can see both halves, as you've got Jupiter shine, not Earth
Yes,
shine,
indeed.
but
That's
Jupiter
true.
shine.
Yeah.
Yeah,
that's
that's
true.
definitely Jupiter shine. Yeah, isn't that a beautiful image?
It is
One of
lovely.
Juno's better ones. One of the planet itself,
Nice.
which
Nice.
is a lovely crescent there. Beautiful. One of Io. Now you've got to remember some of these images are very blurry, and you often hear these conspiracy idiots on social media saying, "Oh, these are all processed images." Well, of course they're processed images. These are the raw images from Juno, and they do need a lot of work with software to bring out the detail. Does anybody know what the resolution of the Juno camera is?
Oh, that's a good one.
What the resolution is? It has a 2 megapixel camera. Only 2 megapixels.
Because it wasn't a major instrument, was it?
No.
No,
No, it was an afterthought, wasn't it?
Yeah.
it's an afterthought. Yeah. But it just goes to show you how long ago these missions are planned, because
Oh, yeah.
a 2 megapixel camera,
Yeah.
I mean, who's got that these days? So these images do have to be processed. They do have to be sharpened and played with to get the most detail out of them. But that is nonetheless a lovely image of Io. And again, you can see the Earth shine on the dark hemisphere, the Jupiter shine on the dark hemisphere. Here's one of Jupiter itself.
Oh,
Oh,
look at
lovely.
Wow.
Yeah. And
That's incredible.
again, just before it's been processed, we've seen the results. I mean, there are some very talented people out there using software tools to bring out the detail and sharpen these images. There's another which is stunning.
Mhm.
a little spot in the corner.
Yeah, and this one as well. I mean, this is like abstract art, isn't it? It's unbelievable.
Imagine
And then this one is much better quality. I think it's looking towards the limb of the planet, and look at that. Look at those storm systems on Jupiter. How beautiful is that?
Yeah.
And
Almost hard to believe.
Sorry, carry on, Aaron.
I was going to say, it's hard to believe that those are natural.
Yeah,
I mean, they're just incredible.
Yeah. What it reminds me of is when you do that, when you get a piece of paper and you've got a tray of water, then you put oil paints on the top, swirl it around, and then
Yeah.
just lay the paper on and pull it out, and you just get these exact same patterns. So
absolutely.
yeah, absolutely. As our Aaron said, absolutely beautiful. They're natural, and these are happening now. It's amazing to think.
Yeah, absolutely.
And they're storms. Remember, they're storms.
They're storms, yeah, absolutely. And that one in the foreground, look at all the swirls and eddies around it.
Yeah, this tiny storms, because they sort of like these smaller storms. If you do a time lapse, they sort of seem to orbit the bigger storm, and sometimes they actually get merged in, drawn into the storms. But yeah, it's amazing because when you see time lapses of Jupiter, and you can see the belts, and you can see all the storms whizzing around and doing all different things. It's fantastic.
So this is actually an image that has been processed by a gentleman called Bjorn Johnson, and you see the difference that the processing makes. Obviously, I think that's stunning. Okay, now let's move over to another planet. Let's move over to Mars. Mars Express celebrated its 20th year orbiting Mars last year. We only just caught up with this, so forgive us if we're a bit late. There's a reason I wanted to show you this, because I wanted to give you some idea of the achievements of Mars Express. Mars Express is a European spacecraft that has been orbiting Mars for 20 years. And if you look at this this image, then you can see on the top row of the figures, it says 10 times longer lasting than the spacecraft's original design lifetime of 1 Mars year. Mm-hmm. That's obviously a mathematical mistake. It should, of course, be 20 times because it's 20 years, unless my maths is wrong. Whatever the figure, it's been there for 20 years. It's traveled 1.1 billion kilometers around Mars. That represents 24,000 orbits. It's had its science operations extended until at least the end of 2026, which is great news, but it has lasted 20 times longer than it was meant to. So hopefully it'll remain in good health.
Yeah.
It uses 200 grams of propellant per year, which is all it uses, which is, nothing really. It's been responsible for the publishing of more than 1,800 scientific papers. It's resulted in 170 plus PhD students being trained. It's collaborated with 12 rovers, orbiters, and landers over its time. It's got 8 advanced scientific instruments, and it was the first European spacecraft to orbit not just Mars but any planet. So, so it's an amazing spacecraft. Sorry, Michael.
Sorry, I was going to say, I was just waiting for you to mention Beagle 2.
Yes. Well, don't mention that.
Don't mention that. Sorry.
Probably a mistake. We'll all get too depressed, Michael.
Okay.
So anyway, the reason I wanted to talk about Mars Express is it's just sent back this amazing image of Mars. Look at this.
Oh, wow.
Isn't that unbelievable? Now, you've got 3 things of interest here. Obviously, in the foreground, you've got Phobos, which we talked about, I talked about quite a lot last week. What else can you see in this image, guys?
Is that
Olympus Mons?
Olympus Mons. Anything else of interest?
Oh.
Atmosphere.
Yeah, the atmosphere. If you look beyond Olympus Mons, you can see the upper limits of the atmosphere. That thin layer. It always amazes people when they look at images of planetary atmospheres about just how thin they are. The Earth is the same, isn't it? When you see an image of the Earth's atmosphere, you see, my God, it's so thin compared to the size of the planet.
Yeah, if the Earth was a basketball, the atmosphere would be a piece of paper.
Really?
Yeah.
Oh, goodness me. So there you are. Thank you, John. That's amazing. But isn't this a beautiful image? Now, I couldn't resist showing you some older Mars Express images of Phobos. How about this one?
Wow.
Oh, that's nice.
Isn't that amazing? Love that image. So this is Phobos over Mars, obviously. A beautiful image from Mars Express. And this one as well. So many congratulations on your 20 years since launch, Mars Express, and many more. So let's hope it continues to bring us great science and images like this.
Yeah, because the on Phobos and Deimos, some of the craters are actually named after Gulliver's Travels, characters and places in Gulliver's Travels.
Because Jonathan Swift predicted the discovery of 2 Martian moons.
Exactly.
Yeah, absolutely true. Not to be outdone, you may remember that there's another country in orbit around Mars at the moment. Does anybody know which one? Apart from America and Europe?
Isn't it
China?
No.
Japan? Japan or China?
No.
No. Okay.
India?
Arabs.
No. Saudi.
Oh, it's the Saudi Arabia.
No.
No.
No. It's the United Arab Emirates.
The UAE.
There is something like that.
With their spacecraft called Hope. And not to be outdone, they've just released this image of Deimos over Mars.
I like that.
Yeah.
Yes.
Which I think is actually, unless I'm very much mistaken, this is possibly the clearest image of Deimos we've ever had.
Certainly looks like it.
Yeah. Which is quite amazing. Beautiful image of Mars's moon Deimos over the planet there from the UAE. The UAE Hope spacecraft has been orbiting Mars for 2 years now, I think. and continues to send back amazing science and data. A big success for the UAE. So many congratulations on that. And they've got more in the pipeline, as it were.
I can remember all the fuss when they went into orbit. I remember now. Could have totally forgotten about it. Yeah.
Well, we did cover it at the time, not the launch, but we spoke about it at the time.
Yeah,
exactly. And there you are. So many congratulations, UAE. Okay, we go much further afield now. Okay, panel, what's this?
Well, wait. This is Aaron.
Dolores,
before you go on, you can go on to that one. Let's stop there for a second. So a couple of our folks that are on the webinar commented on the fact that chart that showed the 10 times, they pointed out, and I agree with them, a Martian year is about twice an Earth year.
That's
and
true.
That 10x its intended lifespan, which was measured as 1 Mars year.
Yeah. Yeah, thank you for that. Yes, actually, after I said that, I did look at that and I thought, oh, I see what it is now. Yes.
Sorry about that.
But it's still an amazing achievement to last 10 times as long.
Yeah.
But then again, spacecraft and rovers have a long history of well extending their lifespan at Mars, don't they? Think of the MERS, the Mars Exploration Rovers.
Yeah.
They just went on forever. So there we are. So thank you, viewers, for pointing that out. Much appreciated. Right, guys. So what's this?
Betelgeuse.
It is Betelgeuse. What can you tell me about what's been going on in recent years with Betelgeuse?
It keeps
brightening
dimming.
and fading.
That's right.
It keeps dimming,
right. There was the great dimming event of 2019-2020 where it got substantially dimmer in the sky, actually noticeably dimmer in the sky. It lost its position as what was it, the 5th brightest star in the sky, something like that. Got relegated for a while. And ever since, astronomers have been trying to work out what was happening. Now, they're pretty sure that it was due to some sort of massive dust cloud that obscured the star. But the reasons for that happening have never been clear. Now a team of astronomers think they know the answer. And this is really interesting. They think that Betelgeuse is a binary star. It has a companion.
Oh.
And this is a team of astronomers, Jared Goldberg, Meredith Joyce, and Laszlo Molnar. And I'm just going to read through this with you. The team, motivated by studies that put the great dimming down to dust clouds, looked at patterns in the star's light curve. That's to say the amount of light that we see from it over time. And we knew already that it had a period, if you like, a fluctuation in its brightness of 416 days because it's slightly variable. But they've now found something else. And they found that it has a longer period where its brightness fluctuates. And usually with situations like this, the reason is that the star has a binary companion that sort of eclipses it from time to time and thus reduces its brightness. And they actually propose that the same is true of Betelgeuse, but it is to do with dust clouds. What exactly is going on here? What they say is, we predict the existence of A or I of B, a low-mass companion orbiting Betelgeuse. This is motivated by the presence of a 2,170-day-long secondary period in Betelgeuse's light curve, which is 5 times longer than its normal 416-day primary or fundamental pulsation mode. While binary is currently the leading hypothesis for these long secondary periods in general, the LSP and the radial velocity variations observed in Betelgeuse taken together necessitate a revision of the prevailing physical picture. So basically, they've looked at it again, having discovered that it pulsates with this much longer period of 2,170 days. What does all this mean? The team, motivated by studies that put Betelgeuse's 2019-2020 dimming down to dust clouds, looked at patterns in the star's light curve. Red giants like Betelgeuse have been found to have these long secondary periods or variations in brightness over long time periods. Long secondary periods have been put down to several causes, with the most favoured hypothesis being that they are caused by companion stars. Based on observations, the team think it may actually be a binary system, which would explain the so-called great dimming event. So there you are. And they think that what happens is that the movement of the secondary star around Betelgeuse causes these eruptions of these great dust clouds. But the companion star is of such low mass that it doesn't actually physically affect Betelgeuse in any other way apart from raising these great dust clouds, which are basically responsible for the great dimming. But the exact mechanism is still uncertain. So that's quite interesting, isn't it? Betelgeuse may have a buddy.
So, yeah, I did see that. Yeah.
So there you are. Okay. So last news item today. I'm sure you all know what this is. It's a solar sail. The idea behind solar sails is that they may provide us with a means of traversing space in the future, because the pressure of light or photons on a very, very, very thin sheet of material is sufficient to give it a kick to move it. And NASA launched an experiment to find out if this actually is going to work. A little while ago, it had real problems up until the moment they deployed it in space, but it worked. So all the problems seem to be behind it. And here's the team before launch. It's 80 square meters in size. And now it's deployed correctly, they will be trying to see if they can get it to move by the sheer pressure of sunlight, which may give us a way of literally sailing across the solar system. And so that's quite exciting. We'll keep you up to date with that to see whether this experiment actually works. Yeah. And that, guys, is the news for this week.
There was only one other story that I picked up on during the week, and that was Bepi Colombo, which is due to orbit Mercury. And they've had problems with its electric engine, its ion engines, and what they've had to do is they've had to change it because it's not the engines aren't working at full power. They've actually moved it so it will slingshot past Mercury closer, so as to bring it back into orbit around Mercury, but it'll be a different orbit from what they expected to do. Other than that, they think all the rest of the instruments are working, but that's the only other bit of news that's found of interest. So it's one of those probes we tend to forget. So it's having a little bit of a problem, but hopefully they've been able to resolve it.
Yeah.
So
yeah, absolutely. Thank you to those of you who are pointing out in the chat that the image of Deimos did look like an enormous arse. I wasn't going to say anything, but I thought I'll leave it to the viewers because somebody will, and sure enough, you didn't let me down. So thank you for that. Yes, it was quite an interesting image. But it was interesting because that is an angle that we've not seen Deimos from before. So we now know that Deimos has an enormous arse, which is adding to our sum of scientific knowledge about the universe. Always worth knowing this stuff. So anyway, we'll move on now. And we're going to go, obviously, straight to Roger, who's going to tell us all about the night sky, I hope, and talk us through this week's gallery, if you would be so kind, Roger.
Okay, so we do have an interesting week ahead, as you will see in a moment. Right, so we are going through from the 3rd to the 9th of September, and here we go through. We've we had a new moon early last night to start off the week, so still reasonably unannounced. Not too much of an interference from the moon should you get any chance to look at the skies this week, which is probably doubtful. This was the moon just a few nights ago before it got to the new moon phase, which was the last time I saw it. And this is the current activity of the sun that was this afternoon. So not too much sunspot wise, but still some activity. But not looking too much on the back, but Daz will fill us in on that later on in the program.
Yeah,
So
nice.
we're currently still got the summer triangle, but that's going over towards the southwest now, and Saturn is getting quite a good show, and that will be at opposition on the 8th, which is on Sunday. So if you've got a chance to see it, it will be magnitude 0.6, and also there might unfortunately, due to the very narrow angle of the Saturn's rings, the Sealinger effect might not be as pronounced as it usually is, which is what usually happens when you've got a few days either side of the opposition where the ice crystals on the ring system seem to reflect most light directly back to the Earth. But obviously with the just a few degrees of angle of the rings, it will not be as prominent, but obviously we will have to see if that can be observed by anybody, which would be a very nice thing to see. And as you can see from the midnight skies, we've got the dominating Andromeda and Pegasus up in the southern skies, and also the Pleiades coming up through with the winter constellations duly following on. So at 4 o'clock in the morning, we've got Orion coming up nicely, and coming through Taurus, we've got 3 planets. We've got Uranus, Jupiter, and Mars, which is heading on towards Gemini for a change. And obviously with Mars coming through, it will be a close object to M35 in the week. And Mercury rising before the sun becomes rather difficult to see just before sunset, but Venus is still quite low and becomes a bit difficult to see anyway because of its clear closeness to the solar brightness of sunset. So good luck with that. But as we can see, it is still a nice challenge to see. So we have got some interesting events through this week. On the 7th, which is on the Saturday, we've got a transit of Ganymede going across the Jovian planet, which could be of interest to those observers. And on the 9th of September, as I said earlier, we've got Mars and the M35 in close proximity to get a photo opportunity should you so wish. Now I'm just covering Sunnishan Atlas on here at the moment because it is getting too low not to be able to see at all at the moment, but it will be getting near its opposition and becoming more bright as it passes through perihelion, and will become more visible through later parts of October. So still keep an eye on that. Still forecasting it to be about magnitude 2, so we'll see how that progresses with that. But as you can see, it's still getting brighter as it progresses through the month of September. Okay, so we do have some members galleries here. Here's one that I took earlier, as we like to say. I haven't done Andromeda for a little while, so I thought I'd go and have a go. And this is a HALRGB image, which was an hour on each filter. And this was just done with my little red cat. So got some interesting colours on there. So one that I haven't done for a little while, but I thought I'd better, because it's rude not to, as it's up quite high in the night sky.
That's lovely.
Yes. And then I went over with some of my photography camera club friends over to Stonehenge because they were in the mood for some more Milky Way. And this is what I managed to get. Fortunately, part of the 303 was closed further westward, which stopped a lot of the traffic going through at night. So obviously there weren't any car trail lights down at the base of the horizon there. So that worked out in its favour. And that one's That one's doing quite well on social media. I've got one group.
I'd like to pinch that one if I can, Roger.
Oh, right. Now, that was just one single frame of 20 seconds there that I processed that with. It was one of the best nights actually there at Stonehenge that I've experienced for quite a while. So
and that was with Samyang as well.
Yeah, that's with the 12mm, which is like an 18mm wide-angle lens, and it's.
Nice.
I did do a landscape version of that, but the vertical one gives you a more definite pattern of the Milky Way.
Yeah, is the light pollution Salisbury or Andover?
That's more over towards the left. So that's probably Andover and stuff like that.
Did you, by the way, did you know they once made a martial arts movie in Andover? It was called Andover Fist.
Oh, right. Where's the mute button? Where's that bloody
Right, okay, we'll move on to Jerry, and we've got a Wizard Nebula that he's taken with 25-minute exposures with his usual filters and processing skills in Pixel Sight.
Oh,
look at
you definitely got the shape of the Wizard Nebula there, yes.
Yeah.
And very well.
Wonderful.
Nice.
Wonderful, Jerry. Very nice.
Yes. Now we've got another picture of the Wizard Nebula later on by a well-known person who used to be on the panel.
Oh.
Okay.
The suspense is killing me.
Yeah, well, you'll have to wait. So we've got another lovely picture from Michael of the sun, which was taken on the 27th of August with his ED80 and his equipment and a lovely spotty sun.
Lovely.
Very nice.
Nice one.
Well done,
Yes,
Mick.
he's
Amazing.
getting the hang of this solar photography.
Yeah, definitely.
Can anybody remember what they call the darkening of the rim? I can never remember the name of it. It's because it's translucent and you can actually see the space behind it. But then as you get towards the center,
it's limb darkening.
Yeah.
Is that what it's called? I thought it had a special name. Oh, that's a bit boring. Oh yes, okay. Then limb darkening.
You could always make one up, Daz.
That's darkening.
Yeah. It's a dazzerarium effect.
Right, now we've got one from Michael Murphy of the Ring Nebula M27 from Sugarloaf in North Wicklow, not Sugarloaf Mountain in
South Africa.
In Rio. Is that right, or is it South Africa? Sugarloaf.
I don't know. No, it might be Table Mountain in.
Or even Sugarloaf lying in Starbridge.
Oh right.
There it is. Sugarloaf in the U.S. too.
So there's the Dumbo.
Yeah.
Amongst the thousands and thousands of stars that
I was going to say that star field is amazing.
Stars.
Amazing.
There's plenty of stars, and there are a few dark regions there that very interesting. Well captured. Okay, so we've got Rachel and Johnny back with their narrowband image of the Wizard, and that's 12 hours with their SHO filters, and this is what we've got.
Oh, lovely.
Oh, I say.
That's lovely.
This was done over 2 nights.
Nice.
As it was over 12 hours. So,
of course.
Yes. There we go. And that concludes the gallery.
Thank you very much, sir. That's absolutely wonderful. I was just thinking, because it's limb darkening, perhaps we should call it the spray tan effect.
Yeah, it could be.
Yeah.
Darken your limbs.
Oh dear. Tony Blackburn.
Yeah. As I was saying, basically the only reason you get that effect is the sun being mainly gas is translucent, so around the edge you can actually see the space behind it. That's where it looks darker. But of course, as you get towards the center, that's where all the action's happening, so it's still bright.
You get a similar effect with the imaging of Jupiter.
Yeah, indeed. Anyway, if you would like to send us your images for our weekly gallery, we'd be very grateful. Pop them in an email address the email to spaceodditieslive@gmail.com, spaceodditieslive@gmail.com. 1 image per email, please, because it makes it so much easier to sort out. And as Roger is approaching his dotage, we have to keep things very, very simple for him. So 1 image per email, please. And if you could put the word gallery somewhere in the subject of the email, that will allow the Space Oddities elves to pull it out and put it in the right place for dear old Roger. So there we are. And we're very grateful. Don't forget, you do not have to have brilliant or expensive equipment to produce great images. Anything you think is worth showing other people, that you would like to share with other people, email them to us. And the standard of images we get, regardless of what equipment is used to take the image, is always very high. So thank you very much indeed. We do look forward to receiving your images. Keep them coming in, please. So let's now talk to Pete. Pete, I gather you have something that you wanted to share with us tonight.
Yeah, I'll give you a bit of background first. Out there on the internet, there are 2 telescope networks. You may be aware of them, you may be not. The Forks Telescope Network and the Schools Observatory Network. The Forks Telescope Network is available to all schools to use for nothing. There are 72-inch telescopes, there are 1 meter telescopes, or 16-inch telescopes in both the northern and southern hemisphere, which school children are allowed to use for free. So that's the Forks Telescope Network. The Schools Telescope Network is the Liverpool Telescope is based in Tenerife and is operated through John Moores University. Now, in my working life, I worked with both organisations, taking images with both observatories. But now, the Schools Observatory and Forks Telescope Network are linking up, which means that all the telescopes, the 72-inch telescopes, the 1 meter, the 16-inch, across the globe are all available to everybody to use. You can sign up for free. It doesn't cost you a penny, and you can use those telescopes at any time. So if you keep your eye on schoolsobservatory.org, keep your eye on there. The 2 telescope networks will amalgamate within the next couple of months. You'll be able to sign up for free. Then you can sit at your computer and use a telescope anywhere on the planet and take images. I just thought you on that. If you need, if you need any information on that, just contact us through Space Oddities, and I can give you all the information you need. Yeah. I know I've retired now, but I'm still kind of got my hand on both networks anyway.
That's great. That's great news. That is, Pete. Yeah.
It is great news because with the Schools Observatory Network, when they're all combined, any astronomy club will be able to sign up. If you're a teacher, you can sign up, or if you're in charge of a group, you can sign up and create your own little group to use these telescopes. Yeah. And when you're using the 72-inch telescopes, when you're taking a photograph, say of the Ring Nebula, you need 1 image with each filter, red, green, and blue, and you're only talking 5 seconds exposure. Oh wow! That's all you need. You don't even have to have guiding switched on. 5 seconds exposure, and you've got a beautiful image. If you use up to 6, go on.
I remember when not so long ago when the Schools telescope, the John Moores one, it was opened up to everybody free.
Yeah, it is. It still is. It still is. Yeah. But with the Forks going into it, because Forks has got so many telescopes across the globe, you've got access to all these telescopes across the globe. So if you've got a cloudy night, you don't want to go out or whatever, or you can't get out. I mean, it's great for disabled people as well. If you can't get out, you've got access to a telescope anywhere on the planet. Just submit your observation.
I shall put the details about that in the next FAS newsletter.
Yeah, get in touch with me. I'll give you all the details.
Okay, great. Thanks, Pete. Yeah.
All right. Thank you so much for that. Thank you very much, Pete. Great news. What we're going to do now is move along for tonight's main feature. And I'm going to talk to you about Big Bang Theory. And just give me a couple of seconds to get myself set up here.
I'll just tell you that it's schoolsobservatories.org.
Schoolsobservatory.org.
Or just do a search on Liverpool Telescope, John Moores University.
Right. Thank you. Okay, so I think we're ready. Right. I hope you can all see that. So what we're going to look at this evening is all about the Big Bang, and never let it be said that we shy away from addressing the big questions here on Space Oddities. And I'm going to tell you about Big Bang Theory, what it is, and how we think the universe evolved after the initial moment of small c creation, if you like. So let's move along with this. And the first question, of course, is what exactly do we mean by Big Bang Theory? So Big Bang Theory is the name given to humans' most successful description of how the universe started. Big Bang Theory makes many predictions that have been confirmed by observations, such as the relative abundances of the light elements, like hydrogen, helium, lithium, and the homogeneity of the universe, i.e. it looks the same in every direction. Well, more or less, but we'll talk about that another time. As an explanation of the origins of the cosmos, Big Bang Theory is perhaps humans' greatest intellectual achievement. Now, if you were to ask people, what do you think humans' greatest intellectual achievement is, you would probably get many answers, but not many people would probably come up with the answer that it's Big Bang Theory, that if we all disappeared tomorrow would remain as the crowning achievement of human thought. And let's see why. There are, of course, still many unanswered questions. Don't get the idea that we know everything. There's still a long way to go in establishing the history of the universe from its inception, if you like, to today. But we've made astonishing steps forward in understanding all that over the last 50 or so years. Let's get a few negatives out of the way first. The Big Bang was not some sort of big explosion, because explosions happen within an existing space. At the moment of the Big Bang, there was no space. There were no dimensions, there was no time, there was nothing. But every time you see a depiction of the Big Bang, a picture of it, in the mind's eye, if it were, this is what you see, some sort of giant explosion. And it wasn't an explosion. And also, it was not possible to view it from outside, as this image does, because there was no outside. So it's a bit difficult to, if you close your eyes and try and think of the Big Bang, always you will view it from the point of view of an outsider. But because there was no outside, that's not how you should portray the Big Bang. In fact, it's pretty much impossible to come up with a visualization of the Big Bang. Very difficult indeed. So you can't blame artists for picturing it from outside, but of course it wasn't possible to view it from outside. So if it wasn't some sort of giant explosion, what was it? A better description of the Big Bang might be that it was some sort of stretching or unfolding rather than an explosion, but even that doesn't really touch it. The truth is that talking about the Big Bang does expose the limits of human vocabulary. We may not have words for exactly what the Big Bang was, and we may never have the words. It's beyond our capability of language to describe it. By definition, the Big Bang gave birth to our universe, so it couldn't have been anything to do with our universe. Whatever the Big Bang was, it was completely outside the laws of physics, because the laws of physics at the Big Bang did not yet exist. You see the difficulty in trying to describe what it was when we can't even use the laws of physics to describe it, because there weren't any. Where did the Big Bang happen? Panel, quick answer to that.
Everywhere.
Thank you. The Big Bang happened everywhere. You often see people asking, where did the Big Bang happen? Can we see where it happened? It happened everywhere. It's just that the everywhere was very, very small. there were no other places for the Big Bang to happen in. It happened everywhere in that tiny, tiny, tiny nascent universe. So we'll just go through the history of how we got to where we are in our understanding of Big Bang theory. And the views of the universe started to change in the early 20th century because astronomers were starting to use advanced technology. New types of measurements became possible, but at the turn of the century, most astronomers thought that the fuzzy nebulae they were seeing through their telescopes were objects within our Milky Way galaxy, because it was thought that our galaxy was the only galaxy in the universe. Nobody knew how big the universe was. It was assumed that our galaxy, if you like, filled the universe. Our galaxy was the universe, which of course we now know not to be true. But in 1912, American astronomer Vesto Slipher observed the redshift of what were still called nebulae, but were in fact distant galaxies beyond our own. He established that they were actually moving away from us. So this was a major discovery, that those what they thought were nebulae in our own galaxy were actually moving away from us. And then in 1927, a Belgian priest called Georges Lemaitre, he's now regarded as the father of Big Bang theory, reading that Slipher's measurements might indicate an expanding universe, although that was obviously just one interpretation because there were quite a few ideas floating around at that point. He reasoned that if the universe were constantly expanding, getting bigger, with all the galaxies flying further apart, if you could rewind the clock, then in the past, the universe was smaller, everything was closer together. Therefore, if you wind the clock back far enough, with the universe getting smaller, the galaxies closer together, eventually you reached a point where everything occupied the same space. And Georges Lemaitre came up with a name for this. He called it the primeval atom. And you still actually see it referred to as that in old textbooks. Some of my textbooks going back to the 50s or earlier still refer to it as the primeval atom. But this was a revolutionary idea because Lemaitre, who as a priest believed the biblical story of creation, in fact that's why he started investigating the history of the universe, because he wanted to see what the Bible said about it and to try and reconcile the two. It meant that there had been a first moment when all the matter and energy in the universe had been packed into an infinitesimally small volume of space. And when God had said, "Let there be light," the universe came into being and had been expanding ever since. So Lemaitre took this as proof, if you like, or vindication that the biblical story of creation was correct, that there had been a first moment, although of course he attributed that moment to a creator. So with these ideas, he went to a conference in 1927 to ask Einstein what he thought of these ideas. And you can imagine he was an unknown priest with no scientific qualifications. He walked up to Einstein, who was sitting on a park bench, sat down beside him and said, "Can I show you this?" And Einstein had a legendary reply. He said to Lemaitre, "Your calculations are correct, but your physics is atrocious." And that really, really made Lemaitre shrink, as you can imagine. So he got really despondent and didn't really push his ideas after that. But to have the world's greatest scientists of the time dismissing you like that must have been absolutely crushing for him. Einstein, of course, did not believe in an expanding universe. He preferred the idea of an eternal, unchanging cosmos, and continued to support this idea even when his own mathematics indicated that the universe is expanding. In a move which Einstein later called the biggest mistake of his career, he introduced a mathematical trick to, if you like, stop the universe expanding. A fudge with numbers he later called his cosmological constant. Needless to say, scientists weren't buying it because it was so obviously cheating, and the properties of this cosmological constant were not consistent with what astronomers actually saw in their telescopes. So Einstein, egg on face, was forced to accept the reality eventually that the universe is expanding. Now, of course, you can heavily criticize Einstein for not following a basic tenet of the scientific method, that is to say that observational evidence is king, And if that evidence contradicts your theory, then you must abandon your own biases in favour of what the data actually says and predicts. But there's an interesting footnote to this. The strange force that we call dark energy, which is responsible for accelerating the expansion of the universe, has properties which are extremely similar to Einstein's cosmological constant. Now, while the jury is still out on whether dark energy actually is something resembling Einstein's mathematical trick, it's interesting to consider that he may have been right all along when he issued observational evidence for his own preferences. Time will tell on that one. And then in 1929, Hubble measured the redshift of around 100 galaxies. These were still called nebulae at the time, as they were thought to be within our own galaxy. What he found was astounding. Whichever nebula, inverted commas, he looked at, its redshift indicated that it was rushing away from us at immense speed, up to 75% of the speed of light. And he realized that he was looking at other galaxies far beyond our own, that our Milky Way was but one of billions of galaxies, and all the galaxies are rushing away from us. At the time, it was not known how many galaxies there were in the universe. We now think it's about 2 trillion, but certainly there were a lot of them that the astronomers were observing in Hubble's time. He managed to measure the distance to the Andromeda Galaxy, the lovely image of which Roger showed us earlier. And it is, of course, the nearest spiral galaxy to our own. And after a few initial miscalculations, when he got it completely wrong, he eventually found that it's more than 2 million light years away from us. And suddenly, for the first time in human history, the true scale of the universe became apparent. After many painstaking measurements, Hubble found a correlation between the distance of a galaxy and its velocity. The further away the galaxy, the greater its redshift and the faster it's receding from us. This linear mathematical correlation has since become known as Hubble's law. No matter where you are in the universe, you would see all the galaxies rushing away from you in every direction. And after this discovery by Hubble of the expanding universe, Lemaitre's idea started to be taken seriously, and cosmologists began to develop what would become known as Big Bang theory. Hubble came to the only inescapable conclusion. The fact that we observe galaxies rushing away from us at ever-increasing speeds, depending on their distance, meant that the universe itself was expanding, carrying the galaxies along with it. And although each galaxy does possess its own intrinsic, if you like, motion, most of the velocity of a galaxy originates from the expansion of space itself. But this idea took a long time to be fully accepted by the scientific community. There were alternative theories which would persist long after Hubble died. Step forward, Fred Hoyle, Sir Fred Hoyle, legendary British astronomer, who coined the term Big Bang in a radio broadcast in 1949. He intended that term Big Bang to be an insult, to belittle the idea, if you like, that the universe had had a moment of creation, because he was a leading proponent of steady state theory, whereby the universe had no beginning and will have no end. According to this idea, matter is constantly being created out of nothing from empty space. Hoyle clung to this idea until his death, despite overwhelming evidence that he was wrong. And if you're not familiar with his work, we shouldn't judge Hoyle too sharply because of his belief in steady state theory, because he was, after all, the man who told us how stars work, and that is what he should be remembered for, rather than this perseverance with a scientific, inverted commas, theory, which obviously went against every last bit of evidence. If you'd like to know more about the life of Sir Fred Hoyle, Daz has created a video in An Astronomical Life series, which you can find on the Space Oddities YouTube channel. It's a jolly good video. I thoroughly recommend it because it does tell you all about the life of this amazing astronomer. And there you are. Now, step forward. American astrophysicist Robert H. Dick, in 1963, he realized, actually, there's one aspect of Big Bang theory that we can actually test. He said that the dying echo of the Big Bang, the last glowing embers of creation, if you like, should be detectable as a wave of radiation permeating the universe. That radiation dates from about 380,000 years after the Big Bang. Since the Big Bang, this radiation would have been shifted to microwave wavelengths due to the expansion of the universe and will have cooled to just a few degrees above absolute zero. This wave of radiation was dubbed the cosmic microwave background, and when it was discovered, it was quite by accident. Now, just as an aside, if you have an old style TV and you detune it between stations, as you know, you get this sort of snow on the screen. Well, about 1% of that snow on the screen and about 1% of the hiss that you hear is the dying echo of the Big Bang. And it's a shame that these TVs aren't around anymore, because I used to enjoy telling people about this in talks I was giving. And of course, youngsters of today, they have no idea what an old style TV like that is. So there you are. So 1% of that snow and the hiss is the cosmic microwave background. And that hiss was what led to an amazing discovery in 1964 by Arno Penzias and Robert Wilson. They accidentally discovered the cosmic microwave background while doing tests on a horn antenna built by Bell Labs to communicate with the new Telstar satellite. It was a hiss that came from all over the sky. And after trying to discount various theories as to what that hiss was, including pigeon droppings in the horn antenna, they actually came to the conclusion, or scientists that they contacted came to the conclusion, that this was what Dick had predicted, the dying echo of the Big Bang. And it was the last nail in the coffin of that state theory, which had absolutely no explanation for this. The CMB had exactly the characteristics that were predicted by Dick in his work. So this was confirmation for the first time that, yes, it was almost certain that the Big Bang had actually happened. So it was a big moment in science. Now, in the late 90s, the COBE satellite, which was put into orbit to try and map this cosmic microwave background, came up with this image. It's a very low resolution image. And by the way, one of the scientists behind COBE was Dr. George Smoot, and a book I think you would thoroughly enjoy. He wrote about COBE and getting the project together over many years. Thoroughly engrossing read is called Whispers of Creation, and if you haven't read Whispers of Creation by George A. Smoot, S-M-O-O-T, you should. What is this showing us? It's showing us differences in temperature of that cosmic microwave background. So some areas in red here are hotter than the blue cooler areas. Differences might only be millions of degrees, but there is a difference which still really needs to be explained exactly as to what it is. Years and technology moved on, and the successor to COBE was WMAP, and this is the 2012 map of the cosmic microwave background. As you can see, it's a lot more detailed, a lot more high resolution, and these are the best images of the CMB, the cosmic microwave background, that we have to date. So we know that this is the dying echo of the Big Bang. And this radiation was released 380,000 years after the Big Bang, when the universe became cool enough to allow photons to pass through it, which they hadn't been able to before that. In other words, the universe 380,000 years after the Big Bang became transparent. And this is the radiation that fills the sky. Since the 1960s, theory has been refined and developed by many cosmologists, and so far has passed every observational test. The basic ideas behind Big Bang theory is that the universe began 13.8 billion years ago in an event that we call the Big Bang. All the energy the universe would ever contain was released at that moment. With the events, time, space, and dimensions came into being, as we were saying earlier. The universe started as something smaller than an atomic nucleus, and the temperature and density of the Big Bang were, for all intents and purposes, infinite. So this is a bit mind-blowing. You really can't comprehend the temperatures and the densities and the energy involved in the Big Bang. Obviously, that energy had to have come from somewhere, but we'll talk about that a little later. At the time zero, all the forces in the universe, the strong and the weak nuclear forces, the electromagnetic force and gravity, they were all united as one force, dubbed supergravity, which would later split into the forces that we observe today. The lightest elements, hydrogen and helium, were formed in the first moments of the Big Bang, with a bit of lithium as well. And the universe has been expanding and cooling ever since the Big Bang. There were, however, some problems. The biggest of these was the problem of temperature. Whichever direction we look in, the universe is more or less exactly the same temperature. So why is this a problem? Well, let me illustrate this. So here you have the young universe with different regions of space. Now, if this were it wasn't an explosion, but let's say if it were an explosion, you would expect different areas of that explosion to have different temperatures. But what we see is actually that they don't. They all have the same temperature, as if they had been in contact with each other and evened out the temperature. But how could this possibly have been true? Well, it came to a guy called Alan Guth, who in 1979 was a junior particle physicist at Cornell. He suddenly realized what the solution to this temperature problem might be. He proposed that a tiny fraction of a second after the Big Bang, the universe suddenly experienced a huge acceleration. And it grew so rapidly that one continuous region of space was able to exponentially expand, and the temperature was thus equal everywhere. So before different regions had the chance to cool down and have different temperatures, the expansion was so fast that everywhere ended up the same temperature. And he called this exponential expansion of the universe inflation. And it was unimaginably brief. After the inflationary period ended, the universe's expansion slowed, only to accelerate again 6 billion years ago with this mysterious dark energy. But that's a topic for another day. So inflation is believed to have started 0.1 seconds after the Big Bang and lasted until 0.1 second after the Big Bang. So it was an unbelievably short period. Now, the effect of this was that, now this takes some comprehension, honestly. The universe is thought to have ballooned to 1 million trillion times its initial volume, by some estimates, in less than a billionth of a trillionth of a second. Now, what this means is that during that inflationary period, the universe expanded much, much faster than the speed of light. That's not a problem, incidentally. The laws of physics say that nothing within the universe can travel faster than light, but there's no such constraint on the universe itself. So the universe exponentially expanded. Well, somebody could do the maths there, but it's a lot faster than the speed of light in that unbelievably brief period. But inflation does explain why the universe is the same temperature everywhere. And this took cosmology by storm because as well as the temperature problem, it solved another of other long-standing problems with Big Bang theory. And since 1980, when Guth published his work, inflation has accumulated a lot of observational evidence which supports it. It has to be said, though, that there's never been a clinching fact in the observations that proves that inflation actually happened. So it's still hypothetical, but it's the best explanation that we have for what happened. But we don't know why inflation happened. We don't know how it got started and why it stopped again. Now, if you ask people about this, ask scientists about this, they'll say that the universe at the beginning of the inflationary period underwent some sort of phase transition, like water changing to ice when its makeup changes. It becomes another substance. So they think it was something akin to that, but what caused it and why is still very much unknown, but there's no shortage of ideas. If you accept inflation and what Guth said, then it leads to an interesting scenario. And what the interesting scenario says is this. Now, for some scientists, it was too much that this inflation was being put forward. It was like Einstein's cosmological constant. It was sort of tweaking the numbers to end up with what you want to end up with. And there are lots of scientists that still think that. However, one interpretation of inflation is that we live in something called the multiverse. And if you follow inflation to its logical conclusion, this must be so, if inflation is correct. Where our universe is one of countless others. In our universe, inflation happened, giving rise to the universe we observe and the laws of physics which dominate it, ultimately permitting the evolution of life. Yet there are countless other universes where it never happened, the laws of physics were different, and life never got started. And there may be an infinite number of these universes, and this phenomenon is called perpetual inflation, where these universes come into existence, and some of them succeed and inflate to be universes like ours, where the laws of physics may be different, but there's a universe, and at other times they may fail altogether to expand. And but this is the logical result of inflation. And we just happen to live in a universe where inflation did happen, life could arise, and therefore intelligent beings like us can ask questions about its origins. So this is an age-old question, why is the universe like it is? And the answer is, of course, because if it weren't, we wouldn't be here to ask that question. But we may live in one universe among many, and that's known as the multiverse. Now, here are the events which cosmologists believe happened at the dawn of the universe. And this timeline is the result of decades of both theoretical and observational efforts by some of the world's greatest minds. All of these events are consistent with what we observe in the universe today. In other words, what had to happen at the beginning of the universe to give us the universe we see around us now? There's not an infinite number of possibilities. What happened during and after the Big Bang is constrained. Scientists hope that with time they can discover and evaluate those constraints and be able to say exactly what happened in the first moments of the universe, but there is a long and difficult road ahead yet. So I'm going to take you through the timeline of the Big Bang. It goes on for a bit, but please stick with it because it's an examination of event after event after event which happened, the result of which was the universe that we see around us. So of course we start at time zero. And what we say here is, something happened. That's about all we can say at the moment. We don't know what it was, we don't know what caused it, because it was outside our laws of physics. So let's just start the universe by saying something happened. It makes it easy. Temperature and density were infinite. The size of the new universe was smaller than an atomic nucleus. Space, time, and dimensions suddenly come into being. At 0 to approximately 10 to the minus 43 seconds, which is 43 zeros after the decimal point, the universe spans a region of only 10 to the minus 35 meters and has got a temperature of over 10 to the power 32 degrees Celsius, which is that many degrees. The fundamental forces of gravity, electromagnetism, plus the strong and weak nuclear forces are united as one force. As I said earlier, this force is called supergravity. But scientists believe this wasn't unstable. It was too unstable to last, like a pencil balanced on its point. Something had to change. 10 to the minus 43 seconds to 10 to the minus 36 seconds was called the Grand Unification Epoch. The force of gravity separates from the other fundamental forces, which remain unified, and the earliest elementary particles, and antiparticles of course, began to be created. Quarks, muons, gluons, electrons, neutrinos, photons, and their antiparticle equivalents. 10 to the minus 36 seconds to 10 to the minus 32 seconds. This was inflation. This was the inflationary epoch, perhaps triggered by the separation of the strong nuclear force. the universe undergoes an extremely rapid exponential expansion known as cosmological inflation. This is one idea, that inflation was triggered by the separation of the strong nuclear force. That's the force that holds the atomic nuclei together. Very strong force. The linear dimensions of the early universe increased during this period of a tiny fraction of a second, by a lot, as we said. So it expands from that tiny size to about the size of a grapefruit in that incredibly brief period. The elementary particles remaining from the grand unification epoch, known as a quark gluon plasma, or sometimes called a quark soup, becomes distributed very thinly across the universe. At 10 to the minus 36 seconds to 10 to the minus 12, this is the what's called the electroweak epoch. As the strong nuclear force separates from the other two, particle interactions create large numbers of exotic particles, including W and Z bosons and Higgs bosons, which you may have heard on before. The Higgs field slows particles down and confers mass on them, allowing a universe made entirely out of radiation to support things that have mass. So that's obviously another important moment. 10 to the minus 12 to 10 to the minus 6 is the quark epoch. Quarks, electrons and neutrinos form in large numbers as the universe cools off to below 10 quadrillion degrees. That's 10 followed by 16 zeros, if I remember rightly. And the four fundamental forces assume their present forms. Quarks and antiquarks annihilate each other upon contact, but in a process known as baryogenesis, a surplus of quarks, about 1 for every billion pairs, survives, and these are the quarks that will ultimately combine to form matter. 10 to the minus 6 seconds to 1 second after the Big Bang, the temperature of the universe cools to about 1 trillion degrees, cool enough to allow quarks to combine to form hadrons like protons and neutrons, which are the building blocks of atomic nuclei. So it was nearly a second after the Big Bang before matter could actually form, atoms could actually form. 3 minutes to 20 minutes after the Big Bang is called the lepton epoch, after the majority but not all of the hadrons and antihadrons annihilate each other at the end of the hadron epoch. Leptons such as electrons and antileptons such as positrons dominate the mass of the universe. As electrons and positrons collide and annihilate each other, energy in the form of photons is freed up, and colliding photons in turn create more electron-positron pairs. It's this imbalance between matter and antimatter that is yet to be explained. If there were an equal amount of antimatter and matter, all of the matter in the universe should have been annihilated. But as we know, there was a tiny surplus of matter over antimatter after this period, which has, as I said, yet to be explained, which has ended up with the universe that we see. Also, during this period, 3 minutes to 20 minutes after the Big Bang, we had nucleosynthesis. The temperature of the universe falls to the point about 1 billion degrees, where atomic nuclei can begin to form as protons and neutrons combine, through nuclear fusion, of course, to form the nuclei of the simple elements of hydrogen, helium, and lithium. After about 20 minutes, the temperature and density of the universe has fallen to the point where nuclear fusion cannot continue. 240,000 years after the Big Bang to 300,000, this is known as the recombination and decoupling epoch. It's a complicated name for quite a simple idea. With the electrons now bound to atoms, the universe finally becomes transparent to light, making this the earliest epoch observable today. In other words, we can't see back in the universe any further than 380,000 years. It also releases the photons in the universe, which have up till this time been interacting with electrons and protons in an opaque photon baryon fluid, as it's called. This is known as decoupling. And these photons, the same ones that we see in the CMB, as shown in the bottom there, can now travel freely. By the end of the period, the universe consists of a fog of about 75% hydrogen and 25% helium, with just traces of lithium. 300 to 500 million years after the Big Bang, the first stars and galaxies form. 9 billion years later, our solar system forms. So that is the end of the timeline. Now, you may say, hang on a minute, surely there's more than one way to make a souffle. Surely you could end up with the same results doing it a different way. Well, the answer to that is, yeah, of course. But to make a perfect souffle, there's an extremely limited set of methods. If your souffle fails, to work out why, you move forwards through each step from the beginning, trying to understand at what point it failed and why the step immediately before the failure went wrong. And then, of course, you then change that step and repeat, make it again, make the souffle again, repeat the process until you achieve perfection. If you follow exactly the same steps to make more perfect souffles, you can say you know what the steps are to guarantee perfection. So, of course, we don't use cooks and chefs to do this. Scientists use supercomputers to run simulations, and they plug in parameter after parameter to see which simulation ends up with the universe or something resembling the universe that we see around us. If the simulation doesn't end up with the universe that we see around us, obviously something went wrong somewhere, and they can trace the step that went wrong, change the parameter, run the simulation again countless times if necessary, which are what computers are good at, of course, and then we end up with a simulation of what we see around us today. And now we can say what steps we need to go through from the Big Bang to generate the universe that we actually see and the behavior that it actually has that we observe. Now, astronomers, astrophysicists, cosmologists and particle physicists have worked together for 50 odd years to establish that timeline, and it is currently seen as the best description we have for the dawn of the cosmos. We now think we know the history of the universe from 0 point, that many zeros, 1 seconds after the Big Bang. And when you think about it, that is an amazing achievement. That is, or may well be, humans' crowning intellectual achievement. And it fits all the observations. It explains why the universe today looks and behaves as it does. It explains the ratio of hydrogen to helium, the abundance of lithium, and there's never been any astronomical observations which contradict the Big Bang theory in any way at all. It is humans' crowning intellectual achievement without a doubt. And work continues at CERN and other places in particle accelerators to try and recreate some of those conditions that existed after the Big Bang, because it turned out that to understand the biggest things in the universe, you have to understand the smallest. There are, however, many unanswered questions. Some of the questions obviously are more philosophical than scientific, but let's just go through some common questions that I've come across about the Big Bang. Why did the universe come into being? Well, my answer to that always is, does there have to be a why? Why is a very human question, because humans are always looking for reasons for things to happen. There doesn't have to be a reason for that, which you may think is sidestepping the question a bit, but I think that's my best answer. It doesn't have to be a why, it just happened. For no reason, maybe. What happened at the Big Bang? We don't know. We need to go back to before 10 to the minus 43 seconds after the Big Bang to trace exactly what happened at the Big Bang. That may never be possible, because obviously after 13.8 billion years, there's not a lot of the early universe left to actually observe. It has to be theoretical work. But anyway, we will see. Did God create the universe? Well, in my opinion, invoking the idea of a creator complicates everything immensely, but it explains absolutely nothing. There's actually no need to introduce the idea of a creator. And that again is humans looking for reasons why things happened, when in fact the universe is completely oblivious to reasons. If there was no God involved, what brought the universe into being? It could have been a random quantum event. You often hear it described as that. Like we see all the time happening with subatomic particles. It could have been the collision of two universes in the multiverse, which is another idea. We don't know, but there's no shortage of ideas. As I said, most are very difficult to study. It's been 13.8 billion years since the Big Bang, and there's not a lot of stuff from that time left to observe. There is zero evidence, however, that the universe was the product of a creator. If we stick to purely what we observe, there's no need to invoke the idea of a creator at all. What started and ended the inflationary period? Well, there are a couple of ideas. We should, introduce the caveat that inflation is still not 100% proven or demonstrated, because, of course, in science you never actually prove anything. It's not demonstrated that inflation happened, but there's a lot of circumstantial evidence in favor of the idea. Will we ever know what happened at the Big Bang? Maybe, but don't underestimate human ingenuity and brilliance. It's got us this far. So, there's still a long and difficult road ahead of us, but don't underestimate the ability of humans to understand and come up with answers to this stuff. It may take 1,000 years before we fully understand what happened at the Big Bang. Who knows? But we've made incredible progress in a short time historically. And there's no reason to think that one day we won't understand exactly what the Big Bang was. What happened before the Big Bang? Well, we talked about this before the show. And as time itself started at the Big Bang, there was no before. Now, this is a bit like asking what's north of the North Pole. It's a meaningless question. Because time started at the Big Bang, there couldn't have been anything before it. Now, the way that I look at this is to say, right, if you have no events, then you have no time, because time is a measure of the passing of events. And if there are no events, then there can be no time. So this is really, I think, why we say that time started at the Big Bang, because there were no events that could be measured by time. However, obviously, something caused the Big Bang, whether it was completely random or not, but something caused it. So you can think that we need to explain that, but in terms of time, it doesn't make any sense to talk of a before the Big Bang. And that is the official scientific answer, and I'm sure people will have things to say about that. So there you are. That is the end of my presentation about the Big Bang. Any questions, comments, guys?
Very nice, Andy.
Thank you.
Yeah, very good, Andy. Very good. Yeah, very good.
Go on.
Yeah, someone's speaking.
I think Michael said something. Did you say something?
We've got an echo.
Okay. Have you got an echo?
Yeah.
Okay, just give me 1 second.
Have I got it?
Has it gone now?
Testing.
Right, okay.
Seems to be better.
Just give me 1 second. I just need to stop sharing. And once I stop sharing, we'll be back to normal. There we are.
Right, okay. Yeah, that's better. That's better, because I was getting I could hear myself talking.
Yeah, we have this ongoing problem. When I use two monitors presenting on one, we get an echo on the sound, and even Restream haven't been able to fix that one. So
I thought the voices were back. The voices were back. That was a fascinating presentation. Cheers, Andy. There's a lot to think about, and one of the hardest things that I find, to be quite honest, and I have done Open University course in the sort of like the beginnings of the universe, using Feynman diagrams and things like that. And the hardest thing is to wrap your head around the minuscule numbers you're dealing with. When you're talking, to the power of the second, how small these actual events are. And then, of course, you've got the other end where you end up with humongous numbers. And it's very, very hard to wrap your head around it. But it's a fascinating subject. It's a bit deep when you go into it. But it's well worth a look. Have a go. Like I said, the Open University do lots of free courses in astronomy. and one of them is the study of the Big Bang. As I said, it's only a short one actually. It's not very long, and thank God for that, because I think my mind would have melted by the end of it. But it just really does. It helps to understand things a little bit better. And you were talking about the multiverse, and there has been suggestions that in the microwave background, when they've looked at it, and you showed the lovely pictures of the map of the thing, that they think they've actually found bruises, which could have been that they hypothesize could have been where other universes, bubble universes, have actually contacted our bubble, but they didn't break through.
That's true.
I'll let somebody else have a talk, so because I don't want to hug it, but I would like to just have a chat in a little while about Roger Penrose, if that's all right.
Yeah, sure. Yeah, viewers, don't forget, if you have any questions, please do put them in the chat. I'd be more than happy to answer them if I can, or the panel can answer them if I can't.
So this is Aaron. I'm a little bit of a rebel. I too have taught. I taught at a college here local in Houston, Texas, in the U.S., and I taught astronomy. And I took exception to some of the things I was hearing, and came up with what I referred to as Clevenson's theory. I don't know that I have the astrophysics background to say these are good theories or not, but I did talk to a local astrophysicist to see if I was out of my mind or if it actually made sense. And so there were a couple things I wanted to mention that are related to your presentation. The first one was, we talked about the cosmic microwave background radiation and the fact that it's not smooth. Well, my personal belief was, if you think about quantum mechanics, nothing is smooth. And if you think about, okay, you get this universe full of energy, and then you have this inflation. Well, any inconsistencies in that original universe are now blown up 10 to the 50th, which is basically what the expansion is. So, it seemed to me logical that a lot of the discrepancies and the just microkelvin differences in that temperature could be due to the inflation of something that wasn't smooth to begin with. And he said that was correct. They have excuses for a whole bunch of the inconsistencies, but not all of them. He said that's a real good possibility for the next one. The other thing I wanted to mention is I'm completely comfortable with the universe being infinite in the amount of energy when it was first created. And, I don't have a problem with that. But what I did have a problem with was there's nothing that I'm aware of in the theories that says it has to be zero. It has to be smaller in size than it is today because it's expanding. So obviously it was smaller in the past. But if it's not zero, let's say it's infinite, and that infinity had infinite energy. So, every little piece of it was infinite. That gets us back to the Big Bang. But there's nothing that I'm aware of that says it had to be at a dimension of zero, or in the case you mentioned, the size of atomic particles.
That's correct. I mean, if you look at all the descriptions, I don't think anybody's claiming it was ever zero, that it started smaller than a proton, but definitely not zero.
Yeah, but see, I'm not even buying that because I don't know of anything that says it had to be smaller than a proton. It just had to be at infinite density. And the other thing I just wanted to mention, this is not directly related, but came up, was the concept of these theories, like the multiverse and other assorted theories. They're all scientific theories, and what I used to strive to stress with the people I worked with in my classes, but also with the public now, is there's a big difference between a theory and a scientific theory. A scientific theory has to be something that's testable and that you test.
Yes.
And as far as multiverses are concerned, as you mentioned, we have no way to test anything related to that theory.
No, absolutely not. No.
Yeah. So, it's a good theory, but we're not ready to call it a scientific theory yet because we haven't started testing.
I totally agree with you. It's pure conjecture at the moment.
Yeah.
It's what the mathematics of inflation say, but as you say, if you can't test it, then it's not a scientific theory. And the same thing, incidentally, applies to string theory. That string theory is all very well and good, but we have no way at the moment with our technology of testing any of it.
Yep. Thank you.
Yeah, that's good.
Any other
Yeah, so
comments?
good ideas there, Aaron.
I've got a query. If we've got the idea of multiverses and bruising signs in the cosmic microwave background radiation indicating colliding universes, does that mean that somewhere we've gotten outside of the universes where the surfaces of the universes are coming into contact with each other?
I think you have to be careful there, John, because if you're talking about an outside, it will be more than our 3 dimensions.
Yeah.
So whether the concept of outside in other dimensions actually works, I can't get my head around that. But I mean, if you think of it logically, then it must mean that there are other universes outside our own.
Yeah.
But it wouldn't be in our normal 3 dimensions. It would be in higher dimensions. So I don't know where that leaves us, to be honest. Anybody else got any thoughts on that?
Well, the only other thing, as I said, if nobody else has got anything just to say at the moment, and it's the idea of that Roger Penrose, of course, the Nobel Prize winner. He's got a theory at the moment, and I first heard him talk about it about what we're 24, about 24 years ago, and his idea is that the universe is created again and again and again. There's no collapse as such, but what his hypothesis is that basically you get the I'm not going to, because this is a continuous thing. It's never ending. So I've got to start somewhere. So basically, you've got the inflation, okay, and then the universe goes through all its history, doing what the universe does, and that's creating solar systems, creating all this stuff, also black holes and everything. But eventually, they all merge together. And the final thing that they can only merge into is a super massive black hole. And eventually, when everything gets to that stage where it's actually been drawn into this black hole, that it will split the fabric of time. And then everything will spill out the other side of the fabric of time. And this will then create another universe. So what it actually started with was the actual everything that was in the previous universe pouring through this one hole. So again, then it all goes out again, does what the universe is going to do, it matures, ends up in a massive black hole and carries on. So you end up with something that looks like a string of sausages. So that's a theory that actually he's still hypothesizing at the moment. But so his theory is that the universe has always been, it does what the universe does, but it ends up in a super massive black hole, which tears the fabric of time, and then boom, space and time, and then it spills through, and you start all over again. So it's never ending, and it's always repeating. So it looks like a string of sausages. That's just one theory.
I mean, much as I admire Penrose's intellectual achievements, and they are many throughout his long and distinguished scientific career, he's been a bit ostracized by scientists over the last few years, especially on his musings about quantum consciousness and things like this. So there are a number of different models where you end up with a cyclical universe rather than one that began and one which will end. I don't know. I mean, I did watch an interview with him, and he was talking about this very thing, and it went several light years over my head, I'm afraid. So I don't know, but thanks for mentioning him, because it's worth pointing out that there are these alternate theories to the evolution of the universe, whether it did begin and if it will end, or whether it's cyclical. What we know won't happen is this idea of the big crunch, which has been an idea around since, well, it's as old as Big Bang Theory itself. That what under this model, what happens is that the combined gravity of all the mass in the universe slows the expansion and actually reverses it, and the universe shrinks again back to this primeval atom that Lemaitre talked about. Thanks to studies in recent years and lots of surveys, we now know there's not enough gravity, there's not enough mass in the universe to generate enough gravity to stop the expansion of the universe. So the universe is never going to reverse its direction. Plus, of course, we now have dark energy, which is expanding that, accelerating that expansion even more. So it's even less likely to happen now. In the news just last week or the week before, a new study has uncovered the first evidence that, in fact, the dark energy, the strength, if you like, of dark energy has actually changed over time, that it may actually peter out altogether one day. It's always been assumed that dark energy has always had a constant value. And a group of astronomers have come up with some evidence which apparently looks quite convincing that dark energy, the strength of dark energy is changing over time. Why this should be, of course, is completely unknown. We don't even know what dark energy is or how it got started in the first place. So we're not going to know why it would suddenly change its value. But that's a road of exploration that scientists will now go down.
Yeah, it's a fascinating story. I mean, of course, then we've got the other end. How's it all going to finish up? As you said, you mentioned the Big Crunch. There's the Big Tear theory, which if that happened, we wouldn't know nothing about it. We'd just blink out of existence. There's this sort of like the cold death theory, where everything, but eventually all the hydrogen will be used up, and everything will just go cold, but it will just carry on expanding. So
yeah. I mean, the heat death of the universe is the current best theory we have. That you're right. The energy density of the universe will shrink to nothing. No new stars will be created. All energy will eventually dissipate and just leave the universe completely empty.
Exactly. Yeah. So we're left with sort of the Big Tear and the cold death of the universe. So on that point, I'd like to say everybody sleep well.
Yeah, absolutely.
But no, it's a fascinating subject.
Ian asked the question, is dark energy converting to dark matter? No, basically, Ian. The amount of dark matter was dictated at the beginning of the universe. Dark energy didn't come along to 6 billion years later. They are, as far as we know, they are completely unrelated phenomena. There's no link between the two.
I think we need to point out something here, that anything that's named a singularity or dark, basically it means we don't know what it is.
We don't know. No,
we don't know what it is, and that's so. Because
there was a thing. Sorry, go on.
I was going to say there was something a little while ago that they actually called dark flow, because everything's moving in the same direction.
Yeah.
And so, but yeah, if you hear the word dark or singularity or anything, they're basically saying that there's something, but we don't know. So
I just pick you up on that, Daz. Singularities at the centers of black holes, for example. We will never know exactly what is inside a black hole. We will never know, because once you're inside one, you can't send any information out of it. So people might stupidly volunteer to fall in and find out what it is. It's not rows of bookshelves, by the way. That's almost certain. At the center of a black hole, what the maths says is that there's this point at the center of the black hole of infinite mass, infinite density, that we call the singularity. Well, all that place is where our laws of physics just don't apply anymore. Yeah. And it's not, don't think of the singularity as a thing, a physical thing. It's just a place where the laws of physics don't really apply anymore. And this is why we need a quantum theory of gravity, because classical science says that, there's a place of infinite smallness, infinite density, infinite gravity. Well, we don't like astronomy, infinities in science, which is why I said earlier about the temperature and density at the Big Bang, for all intents and purposes, infinite. Because what are there any actual infinities in nature? I certainly don't think so. When we say that the temperature and density at the Big Bang was, for all intents and purposes, infinite, it means that it was so high that it's off the scale. We can't measure it, but it doesn't literally mean that it was infinite, because what does an infinite temperature mean? Because if you've got something that's infinite in temperature, you can always have infinite temperature plus 1 degree. And so on and so on. It's all this whole ancient argument about the nature of infinity.
I mean, you talk about infinite things, of course, being massive, but then again, also mathematicians and physicists don't like zero.
No, that's right.
So
That's
it's
well, the Romans certainly didn't.
No.
Listen to them; they knew what they were talking about. Right, guys, we need to be moving on. So, any other thoughts or comments before we move on?
Just on your infinite, I suppose if the energy density of the proto-universe was infinite and it expanded, then the energy would still be infinite, and then it expand a bit more, and the energy density would still be infinite.
Very true.
It was truly infinite.
Yeah, that's right. Very true. Yes, because you can't destroy that energy. It's always going to have the same amount of energy. There we are. So we will see. David in Grand Prairie, Texas. Nice to see you, David. David's got a question about Starliner, actually. Could they just jump? No, seriously, this is a good question, David. Thank you for that. Because what was the name of that guy who jumped out of the?
Baumgartner.
Yeah. Baumgartner.
Yeah. Yes, he did, didn't he? He jumped.
He did, yes.
But the space station is a lot higher than that.
Yeah. It's still going 25.
From.
They're still going 25,000 miles an hour. They've got to slow down from as well.
Yeah,
he wasn't going that fast.
No,
and they haven't got a heat shield.
Yeah.
Make a nice little.
Impossible. I mean, you would just be going too fast when you got to the ground. You would slam into the ground and create a fairly sizable crater, I would think. I don't think you could slow down enough coming through the atmosphere.
Well, I suspect you wouldn't make it to the ground because you don't have a heat shield, which means you'll
Exactly. So what height does the space station orbit at?
640 miles in it.
Yeah, something like that.
640 miles.
I know Polaris Dawn's going to be 3 times higher, isn't it?
Yeah. So you could work out the velocity that you would have going through the atmosphere. You would burn up like a meteor.
Yeah.
Nice, but thank you for that. Thank you for that, David. Nice to see you. Okay, well, let's move on. I'm going to go over now, before we get to Daz's Solar Watch, I'm going to go over to Michael now. Now, Michael is going to tell you all about, we've mentioned it before, but Michael's going to give you a bit of detail about a new Space Oddities publication. Before I forget, can I just mention before you start talking, Michael?
Yeah.
If anybody would like that presentation on the Big Bang that I did tonight as a PDF file, if you'd like to have that with all the text in it and the images, just send us an email at spaceoditieslive@gmail.com, because I've actually saved it as a PDF as well. So if you'd like a copy of that, send us an email, put something like Big Bang in the title, and I'll mail it to you. So there you are. Anyway, off you go, Michael.
Right, thank you. Just bear with me. I need to sort my screen out. Yes, I've got that now. Right. I want to talk to you about a magazine called Capcom, which I've been producing now for the last 30 years or so. Back in 1990, a few people got together and formed the Midlands Spaceflight Society in the UK. We used to have meetings in Birmingham every 2 months. The founders were spaceflight author David Shaler and astronomer and author Andrew Salmon. We wanted to bring quality spaceflight talks to the Midlands in the UK, so members didn't really have to go down to London. Most of the talks at that time were done by the British Interplanetary Society in London, and it wasn't a bit of a jaunt to get down there in that time. So, and this is the latest cover for Capcom, and as you can see, the main topic this time is the Starliner troubles, with an original article by a good friend of mine, Ben Evans, also based in the Midlands. He's done quite a lot of research on this spacecraft, and it's all up to date with the latest decisions on with NASA as well. So that's Capcom. And now, as I say, Capcom, the Spaceflight Society was created in 1990. But we also discussed having a newsletter which turned into Capcom, and the first issue was created in September 1992, and this is a copy of the original first issue cover. You can see the difference in the quality of the newsletter. Originally, this was at the time when word processors for home computers were only just coming about, really. And I actually had one of these, and I started producing the magazine on that, and it was just 4 pages long, and I've enjoyed doing it ever since.
Michael, can I just ask you, because I'm kind of nostalgic about these things, can you remember what software you used?
Good question. I'll have to try and dig it out because I just can't remember. It wasn't Word. It was something before Word.
WordPerfect, maybe?
It might have been WordPerfect. That rings a bell.
Yeah, because I actually used to teach desktop publishing with WordPerfect courses.
It might have been that.
It looked kind of familiar, so
yeah,
I'm guessing it's WordPerfect. This is not at all important, so please carry on.
No, that's okay. And as you can see, what we tried to do as well, you can see from the title of that cover, we used to try and go to places to get the information, because at that time, obviously, the internet was in its infinity. Most of our information came via press releases that a few of us received through the post, and we copied the information into magazine from those. And that first issue was at the time of the STS-46, and I went to Darmstadt in Germany with Andrew Salmon, and we had a few days in Darmstadt to cover the mission, the shuttle mission at the time. So that was quite an interesting time. Okay, so unfortunately, although the society kept going over the next decade or so, our founder Andy Salmon was lost due to a long interests. Meetings continued, but they actually began to struggle. Andy was really the driving force for the meetings at the time, and a lot of you will realise it does take a lot of people sometimes to organise these sort of things. But there's not always many volunteers that come forward to do that sort of thing. So Capcom continued as a magazine in its own right, still under the within the Spaceflight Society name, but that continued until 2020, when we decided to close MSS after 30 years. I was hoping to bring Capcom to the commercial market. I took early retirement in 2018, and I wanted to try and do this commercialization of the magazine. I formed Go Space Watch and tried to bring in Capcom into the commercial world. So that was 2020. In 2022, Space Oddities was formed, but also at that time, unfortunately, I had to close Go Space Watch due to personal circumstances. So commercial side of this venture didn't really get started because of my personal circumstances, basically. So, and now we have decided that the Go Space Watch is going to be no longer a name on the top of Capcom. I discussed bringing Capcom into Space Oddities with the team, and it was welcomed. The idea was welcomed, and this September, the first issue of this volume is under the Space Oddities name. Also, we decided not to continue printing the magazine because of various reasons, including costs and actually getting the printing done itself. So we've decided to drop the printing side of it. Capcom will be just a PDF download, and it will be free to anybody who wants to read it. So basically, that's all about Capcom, and we will make it available to everybody. I think that's the last slide. It is, yes. Okay. I haven't got a link for you at the moment, but what we'll do is, if you want to send, if you want to download it, if you send an email to the Space Oddities email address, I'm sure we can sort out a download link for you to actually download it onto your machine. But as an aside to that, although it's free to download, there, as Andy said earlier, there is a cost to us to produce this, such as software and that sort of thing. We would like to have donations, not just for the YouTube show, but for the production of Capcom as well. So
Indeed.
if you like the magazine, it would be good to get some donations in as well. So
if you would like to make a donation to Space Oddities, we've already mentioned that you can, of course, buy us a coffee, but if you'd like to give us an actual donation, you've got the super chat icon under the chat window, which is the dollar symbol. You can click that if you wish to make us a donation, which, you know, as I always say, you're probably fed up with me saying it by now, but I'll say it just once more for time's sake, that all of the money that we receive goes towards creating things like Capcom, keeping the Space Oddities going, paying all the fees that we have to for software and whatever. So we're not living in Bermuda on a yacht somewhere, unfortunately, but we probably never will be. Actually, I can think of better places to go than Bermuda. So
but we dream.
Yeah, absolutely. Yeah. David in Grand Prairie says, "I remember the NASA Who's an 8x10 glossy photos and patches by the mail."
That's right.
Absolutely.
Yeah.
I had a set of Voyager photos.
Yes.
From the Uranus encounter. I've still got them, actually.
Yeah, brilliant.
With all the details on the back. Great days, David. Great
I'd like to say that we all do this for fun, and we love doing it. It's
fun, is it?
It is, yeah. Right. You know, so you know, we'd like some kind of donation if you can do. Great. So thanks very much. Yeah.
Right. Okay. So that will be a new Space Oddities publication. What we might think about as well, Michael, is perhaps offering it as a file on the Facebook page.
Yes, that's an idea. Yeah,
which we can also discuss.
Well, that's an easy one to do anyway. Yeah.
Yeah, absolutely. But everything has a cost, so your donations, whether it's through a super chat or the other methods there you've got of giving us a donation, we would be obviously very grateful, because some of the software fees we have to pay are quite substantial.
Yeah.
Luckily, they only come along once a year, but we have to save up for them. So there we are. Okay, right, Michael, if you could just stop sharing your screen.
How do I stop sharing that now? Sorry.
Just click the share icon again.
Share. Which is what? Oh, hang on. Why can't I close this? Oh, you've done it.
There you are. Okay.
Okay.
Right. Now, that brings us to what many people see as the highlight of the show, because they're mad. It's Daz back with his solar-powered watch. So Daz's solar watch.
Before we start, there's a question. Now, it came up and it was sort of like blocked, and we had to release it. But it hasn't come up on the chat on the right over there, and it's just popped out the way. Let's see if I can find it again.
What are you trying to say?
It says Kenneth. It's from Kenneth Holmedal. I hope I pronounced that right. If I didn't, I do apologise. Does a black hole have a backside, or does it suck in from all sides?
Oh, can I take that one?
Yeah, of course, Aaron. Go ahead.
Okay, so a black hole is a collection of mass that is so massive that it wraps space-time around it. So the question of is there a backside doesn't really have an answer. And the other thing I wanted to mention, which is why I grabbed it, was black holes do not suck.
No.
If you get too close to a black hole, you get pulled in, just like if you get too close to Earth, you get pulled in. But
yes,
anyway,
a lot of people have this idea that black holes are like cosmic vacuum cleaners, sucking everything in their path. But it's gravity, it's mass. It's no different from any other object with mass. Everything with mass has a gravitational field. It's just that the black hole has so much mass that it's a strong gravitational field. But it doesn't behave any differently from a planet or a star or anything else that has mass.
Yeah,
So,
one way that you can think about it is if the sun, which it's not going to do, but if it were to magically turn into a black hole, the Earth would continue to orbit around it forever.
Yeah, absolutely.
It would be cold and dark, but we'd still be here.
Yeah, absolutely. Yeah, if you replaced, not that there is a black hole with the mass of the sun, because that's not enough mass for a black hole, but if there were a black hole with the mass of the sun, replace the sun with the black hole, nothing changes. As you said, be dark and cold, but nothing changes. The planets would continue in their orbits as they always have. So Simon says, I was this old when I realized that a black hole wasn't a hole in space, but a sphere. Yeah, absolutely. And don't forget that classic line from Star Trek, which, is fingernails down a blackboard time, when somebody on the bridge of the Enterprise says, "Captain, the black hole's event horizon has got a crack in it." And that immediately caused me to throw a beer bottle at the television. Luckily, I was so drunk I missed, but there we are. So there you are. Yes, thank you for that, Simon. Yes, it's not a hole in space, as you now know. It's a sphere. So there you are. And it's a sphere, of course, because that is the natural shape for anything that's in hydrostatic equilibrium, as it's called. So everything mass gets pulled into a sphere with enough gravity, which is why we have asteroids that are not spheres, because they haven't got enough gravity.
And wasn't a black hole a star at one point?
Maybe.
Yes. It depends what type of black hole you're talking about, though. Stellar mass black holes, definitely. Supermassive black holes, no.
Yeah.
Well, there was a phrase going back in time with really old astronomers. When I'm talking about sort of like 300-400 years ago, where they talked about dark stars rather than black holes, and they think that, and when you read into it, what they're trying to describe is a black hole. It was an Englishman. He was a reverend. I can't think of his name. And there was a French chap, both talking at the same time. They were contemporaries, and they were talking about dark stars. So we might bring that up sometime. So
and incidentally, just out of interest, in Russia, they're not called black holes.
Oh.
They're called frozen stars, because in Russian, black hole means exactly what you think it means. So they don't call them black holes; they call them frozen stars. Just thought I'd throw that in. Trivia for you. So there you are.
Interpretation.
Yeah, absolutely.
Right,
all
we're
right.
getting on a bit, so I'm going to have to
getting on a
rush
bit.
through
We
this.
need to get Gaz fired up and firing on all cylinders.
My Horlicks is getting cold.
Yeah.
Yeah. Right, so there we go. Can everybody see that?
Yeah.
Yeah.
Can you move your mouse
just
around? See your cursor as well?
Right, I'm assuming I'm on.
Yep.
Can you see my cursor? Yep.
Yep, that's there.
Right, okay, then I'd like to start with this. This week has been up and down all over the place. The sun has been active. It's not been hyperactive. We've had no X-class flares or anything like that. But we've had some lots and lots of, and I mean really lots of C-class flares. But towards the end, we've also been getting some M-class flares. But as you can see, because of this, and we had some coronal holes giving us enhanced wind. And as you can see, this is for the UK. You can see we've got 3 data points, and all through all of them, all through the week, we've been up and down all over the place. The actual magnetosphere that protects us is ringing like a bell. It hasn't had a chance to settle down, so anything that comes towards us has a better chance of coming back into our atmosphere and giving us aurora. We had in Shropshire here, we've had 2 sightings of the aurora this week. You can guess where one of them was right at the beginning of the week, and then you can see where the second was. It was around about the 30th and the 31st, and the alerts were going off. I popped outside on the 31st, early hours of the 31st, took a snap, and it was there. But it was so faint that when I tried to put it on YouTube, on Facebook, it wasn't going to have it. The algorithm just completely took the color out, so I didn't post that. But yes, as you can see, lots of people all over the world, around the world, have been enjoying some auroras, quite low latitudes. So if you saw some, great, absolutely fantastic. I did see some pictures from Yorkshire, and it looked absolutely beautiful. So yeah, so this week has been a very, very interesting week, and as you'll see as we go along, I'll try and rush through this as fast as possible. So here we are again on the left hand side. It's the 27th. That's what we left last week. On this is the 3rd of September. We've gone from 11 active areas to 10. But this number of sunspots is around 200, which was exactly the same as last week. The only thing I will ask you to watch when we go through I might snip through some of the movies because we've been saying, is watch this area 3807. Now you should be asking yourself, what's it doing over here when 3806, which comes before it, is over here? Well, what it is and you'll see it in a minute, is that it actually grew while it was on this side of on the Earth sides. So I'll just move on. So here we are. So here we are on the 28th. If you look for 3804, where my cursor is, just above it here, there's a little black spot. I don't know whether you can see it. I can see it. But there's a little black spot, and you'll notice also it's above 3804. We come across the 29th, the little dot's got a little bit bigger. Come across again to the 30th. Look, we've got these spots all appearing now. So within 48 hours, we've now got a pucker sunspot region. But look again, it's still not numbered. And it's not until we get to the 31st where they've actually numbered it. Of course, we've moved on since then, and all it's done since then is grow. And it's been giving us quite a few nice little low-class M-class flares. And it won't be long before it'll actually be disappearing off the side of off the western side. But also, just going back to the 31st, look at this group that's all coming around here. And I'll talk about this in a second. So I'll move on again quickly. Right, here's the first one. This is, of course, we're looking at the magnet. In the 9 o'clock, you'll see a first flare. But what you need to be looking at is about the 8 o'clock region. When we get to about the first, if you look at the timer counting down, get to the first, you'll see a sudden flare off at the 8 o'clock region. But look at all these loops on both sides of on the western limb, on the eastern limb. And there's even some activity going down in the southwest. Now, see that big bunch of come up there? That was a big CME that flew off. It's not directed at us, but it could give us some fun and games later. But again, sorry, I meant to think, it was to watch 3807. So we'll go on to the next one. So, of course, 3807, here it comes here. Look at it just round here, and you will see that grow as the week goes on. So again, this is in 304 Armstrongs. So again, but we'll look for the first again, and you'll see this big expulsion at the 8 o'clock region. But look at all this magnetic action going on, coming in from the eastern side. It's now stretching from the center of the sun all the way to the eastern side, and it's still not finished. There goes your flare. We'll see that a little bit better later on. And look how big 3807's getting, and it's also slipped below now. What was it? 3806 was it? If I remember right. So that's that. So I've got a couple of these, so I do apologize. Now this will show you the chronograph. This will show you the big expulsion of the material. That's not it. That went off at the 9 o'clock. That's when all this stuff was on the backside. Now what we'll do is when we come up to, like I say, watch the clock at the bottom. When it gets into the 1st of September, just watch the 8 o'clock region. Most of the stuff you're seeing now is all stuff that's happening on the far side of the sun. So here we come. We're coming up to it. Bang! Look at that. And that was all directed towards Venus. There was a. I will show you. Well, I'll show you a bit later on, quickly. What? Where's me? There you go. A bit more all that in detail. And just, I think this is the final one. So this is 131 Armstrongs. This gives you a chance to see all the little flares going off. You'll also, again, watch 3807 forming here, and you will see that it really starts to throw off a couple of big flares. There's lots of stuff coming around here. In fact, when this finishes, it's actually in mid-flare. You'll see it right at the end. But you can see all these flashes. You can see some of the magnetism involved. We're going to see the big flare in a second, coming down off the 8 o'clock region. But yeah, and again, you can see all this magnetic action appearing now on the eastern limb. And virtually, in the end, I'll show you some more pictures, magnetic images, and you will see that how far this extends. Yeah, we're nearly finished. Boom, there goes the flare at the 8 o'clock region. And then when this finishes, you'll actually see 3807 actually flaring again. It'll actually start. There you go. You can see it there. It's a nice bright flare. So we'll move on. Now, as I said, this is what I showed you last week. And I was talking about this big blob here of magnetic action going on. And this is when it was still on the far side. Remember, this is the eastern limb. This is the face of the sun, the Earth facing Earth. So this is the eastern limb. All this stuff is coming towards the actual limb itself. And of course, it's coming along, and this is all on white. I can't see my arrow. There it is. So now these are magnetic images. And you can see, now look at all this. All along the southern hemisphere, you've got all this magnetism actually happening. The actual blob itself was this from around this sort of area, but it's still coming. There's a little bit still to come round. But as I said, 3807 has grown, and it's got more and more busy. 3808 has been giving us some nice action. But now the big player is it 3813, this one here. And this is the one at the end of the week has been giving us some medium class M flares. So we should have some more stuff possibly on its way. We haven't got any coronal holes, so to speak of. So, but there is a chance that there's some high coronal thing. Now, again, this is a close-up of this eruption. Look at all this reconnection going on. It's absolutely fantastic.
Look at that.
And then what will happen is, as soon as this one finishes, snip over to the one on the left, to the 304 Armstrongs, and you will see it. It will start automatically. There it goes. As soon as the other one finishes. Now you watch this. You can see the plasma flowing up through the bands of magnetism through the arches. There's even connectivity. This is the same sort of thing we were looking at last week. So yeah, is all this, and this was going on. These are actually covered by 12 hours, and they were still ongoing when I decided to cut it off, or else we'll be here all night. I mean, I could sit there and watch these things all day. So next thing we do is we've got This is the close-up of the boomph. There it goes.
Oh.
And as I said, this is heading towards Venus. Now, it's a real shame because I would have loved to there being some sort of orbiter around Venus to see how Venus interacts with this massive storm coming towards it. Remember, Venus does not have a magnetosphere. It has no magnetic field to protect it. So there's a good chance that this could strip some of Venus's atmosphere.
Do you mean to say that the penguins are in danger?
Yep. Yeah, those penguins in the high atmosphere are in danger. So no more phosphine for us. But yeah, it would have been nice if we could have. I mean, it's c'est la vie, it's the way things are. If we had a probe there, we could have probably seen some interaction, and it probably would have. If we could have seen it happen, we could have then extrapolated that to Mars and things like that, where all this other things, where the atmospheres have been stripped by the solar winds. So yeah, if we'd had something there, we would have been able to see it. So I don't think there's much more. Let's just click on. Right, now here's some cactus images. You can see all this matter being thrown off. We had 3 events that actually happened in 3 different, in virtually the same time. If you go to this cactus site, you'll see there was 3 events, and this is why I've got, this is actually showing an event that's coming off this way, because this is the way that it wasn't following, and this is what you see. Everything's now calmed down, but I'll keep on talking to you about halos, and this actually produced a halo, so we could get a side swipe from this. And what I'm talking about a halo is, oh no, go back, getting too excited, go back. Okay, can you see this faint white line coming around here, and then it comes back in here? Very faint. That is the halo. That's the shock wave. And it shows us where basically how big this event is. And if we see a shock wave, if it's for 360 degrees, we know we're going to get some. And there's probably some more of the shock wave underneath here, but you can't see it. So that's what I mean. And this is why I say you've got to look at this in all wavelengths, because what you can't see in one wavelength, you will see in these wavelengths. And as you can see this shock wave here. And that's when I'm talking about a halo. That's what I mean. You're looking for this very faint thing. And so, like I said, sometimes it'll go 360 all the way around and so and so. So I'm waffling, so let me get on. Right, so what's coming? All right, we're supposed to be getting some enhancement today, but it's not going to amount to much. We have got some very high wind speeds, which will keep people interested up in the Arctic and the Antarctic, inside the Antarctic and Antarctic circles. They'll be getting possibly some nice auroras. As I said, the Earth's magnetosphere is still rattling. It's unsettled, and it'll take a little while to calm down. But while we've got all these M-class flares going off, it's going to be hit time and time again. Only glancing blows. So just listen for your alerts going off and just jump outside, point your phone north and see if you can catch anything. But as you can see, we've got some high winds coming from not some coronal holes, but yeah, we've got some stuff coming towards us. And there is a little bit of radiation stuff here, the plasma density, but it's not very high. Look, it's just above 10. So don't expect anything, but then again, you never know. Right, the results are in for August. I know you've all been waiting for this with Pensive, and look, we're still on the up.
Yeah.
So wow. The value, the monthly values is 2015. It's sort of, there is a formula how they work all this out. Predicted values were 107.8, but yeah, we've gone beyond that. And as you can see, we're now way above what 24 was. And just to put this in a bit more perspective, here's an extended view. This goes back to cycle 22. So we're almost coming up to rival 23. And remember, we got double peaks everywhere. So because one of the things I would like just to pop back and say to you is when we get back to the magnetic images, where are they? Come on, come on. Come on. Oh, how far back are they? Here we are. Have you noticed that how all of this stuff is virtually all in the southern hemisphere?
Yeah.
Remember when I said that hemispheres do not interact with each other? They're separate identities. And I said the double peaks is when one sphere finishes its cycle, and then the other one will carry on and start doing another its own peak thing. And it looks like this is what this is. I can't say that's what it is, but to me that is a definite. And also, again, as the week goes on, anything that is up here is being pulled towards the equator, which is usually a sign that we're coming to the peak. So I think I'll leave it there. I don't think I've got anything else on the end. Let me just have a look. I do apologise for this. I wish I hadn't put the smooth interchain thing in because it takes the time. So trying to be clever. So one more, and let's see. No, that's it then. Thank you very much. Let me get out of here.
Okay, right. Thanks, Daz. So, not a spectacular week on the sun, but still plenty of activity. And those sunspot numbers are well above the predicted values.
That's right. As I said a couple of weeks ago, we were way up into the mid 300s for a few days, which has really pushed them up. So,
amazing.
Yeah, the sun's doing its own thing at the moment. As I said, I was talking about last week through helioseismology. They think that they're now beginning to recognize a pattern where the sun, cycle 26, is beginning because of what they've looked at in the past and all that. I don't see it myself, but they're going, I don't know enough about it. So, yeah, okay then. Bye, Pete. Sorry. But
right,
yeah, okay
just,
then.
sorry.
Oh, you carry on.
Can we just say on behalf of Pete and John, they've had to go, unfortunately. I see Anne and Mick are going as well in the chat. So lovely to see you both. Hope to see you in the flesh, as it were, before too long. So that's it for this evening. Now, next week we will be back, of course, at our normal time. Not quite sure with what yet, but we'll work something out for you. Don't forget that on Friday morning, we have the launch of the Polaris Dawn mission, subject to change, of course, because this mission has been delayed and cancels more times than I've had hot dinners. So at the moment, it's due to launch at 8:38 BST, and we will be going live at 8:15. Yeah. And we'd love you to join us for the launch of this historic mission. Look on the channel and you'll find a video about the mission objectives and about the crew with their biographies, which we've talked about, hoping that the launch was actually going to happen. So we're not going to do that again because we've done it. So do join us on. And then Friday evening, of course, we've got the undocking of the Boeing Starliner from the International Space Station, which should be okay, but there's a possibility it won't be. So let's keep our fingers crossed for that. And then a few hours later on, in the early hours of Saturday, which we hope you can join us for if you're insomniac and you've got absolutely nothing better to do, or if, like Michael, you've been gallivanting all night and you've just got in after a night on the tiles.
Having his bacon sandwich.
Yeah, that's right. He'll be eating his bacon sandwich. Then if you can join us in the early hours of the morning, we've got the actual landing of the Starliner, which will be the end of this disastrous mission. It's been disastrous both for Boeing and for NASA. An absolute nightmare of a mission. So anyway, so we hope you can join us for those live events.
And also, if I can just say, if we're possible to show it, hopefully on Monday, there should be the first commercial spacewalk. Everything permitting. But we may not be able to show it because if you remember when they did Inspiration 4, they didn't show anything that was happening because it was made into a movie afterwards. So we may not get to see it, but I think because it's so important, I think SpaceX may overrun. I mean, it's their spacesuits anyway.
Well, that's right.
Yeah.
So we will see. But we hope you can join us for the launch of the Polaris Dawn, the undocking of the Starliner, and the Starliner landing later in the week.
Yeah.
The live streams are up on the channel now, so you'll get the full details there. So that's it. So I'd like to say thank you to all the panel. Thank you to Michael. Thank you to Daz. Thank you to Roger. Thank you to Aaron, joining us all the way from the States.
Ian, it has been moved to Friday. It's not tomorrow.
Yeah.
It just popped a question into you.
Yeah, it's been moved again, Ian. So so there you are. Yes, and there are posts on Facebook, Ian, that I wrote this morning with the details. If you look in the events, all the details are there in the events on the Facebook page. Don't forget our Facebook page, Space Oddities Live, for subscribers to the channel. If you're not subscribed to the channel, then why the hell not? Just click the subscribe button. Do click like and as well, and leave a comment in the video comments, and rather than in the chat, because they don't count towards the number of views. So only likes on the actual comments in the video on Facebook get counted. So we'd like to say thank you very much, and from all of us at Space Oddities, have a fantastic week. We hope to see you later in the week. Keep an eye on the Facebook page. I'll keep you updated there if there are any changes to the projected events that we're planning to cover live. But if we don't see you, we'll see you back here same time next week on Space Oddities. Thank you so much for being here. Thank you for your donations. And from all of us at Space Oddities, have a fantastic week. Take care of each other. Stay safe. We'll see you next week. So from